Have you ever stopped to think about what's actually happening inside your computer when you're playing a game? The power packed into a modern graphics card is, well, it's just mind-boggling. We think we know what fast means, but what these things do every second is on a whole other level. So let's pull back the curtain and see how it's all even possible. Okay, get ready for this number. To run a game like Cyberpunk 2077, your graphics card has to perform about 36 trillion calculations. And that's not per minute or per hour. That's every single second. 36 trillion. It's a number so big our brains can't really even process it.
So to try and wrap our heads around that, think about this. Imagine every single person on Earth, all 8 billion of us, doing one math problem. Now, imagine doing that on 4,400 different Earths all at the same time, every single second. That's the sheer force we're talking about, happening inside that little card in your PC. Which begs the question, how in the world is that possible?
To get to that answer, we really need to understand the scale we're dealing with here, and just how fast the demand for this power has exploded.
Just look at this timeline. It's insane. Back in 1996, Mario 64 felt revolutionary, and it was running on 100 million calculations a second. Fast forward to 2011, and Minecraft needed 1,000 times more power, 100 billion. But today, we've jumped another 360 times past that. This kind of exponential leap meant we needed a totally new way of thinking about how computers work. And that new way of thinking becomes crystal clear when you compare the GPU, the graphics processing unit, with its more famous cousin, the CPU, the central processing unit.
Okay, this is probably the best analogy for understanding the difference. Think of your CPU like a jumbo jet. It's incredibly fast, super flexible, and it's designed to handle all sorts of different, complex jobs, one after another, really quickly. It has just a few very powerful cores. A GPU, though, is like a massive cargo ship. It's not as fast, but its sheer capacity is unbelievable. It's built for one thing and one thing only, moving thousands of identical containers all at once. It does this with thousands of simple little cores, each one a specialist at doing the same repetitive math problem over and over and over again.
So, what does this giant cargo ship actually look like up close? Let's zoom in, way in, and see how a modern GPU is actually built.
We're starting at the heart of it all, the GPU chip itself. A chip like this one, the GA102, is made from an almost unbelievable 28.3 billion transistors. But they're not just thrown together, they're organized in a really clever, hierarchical way. So, at the highest level, the entire chip is split into a handful of big sections. In this case, we have 7 of them, and they're called Graphics Processing Clusters, or GPCs. You can think of these as the main districts of a giant city on the chip. Now, let's zoom in on one of those districts. Each GPC is broken down even further into 12 smaller units. These are called streaming multiprocessors, or SMs. So now we've got dozens of these smaller processing neighborhoods scattered across the chip.
And this is where we finally meet the actual workers. Inside every single one of those SMEs, you find different kinds of super specialized cores. You've got your CUDA cores, which are the basic workhorses, the simple calculators doing most of the gaming math. Then you have tensor cores, which are geniuses at the kind of math needed for AI. And finally, RT cores, which are built specifically for the crazy complex math behind realistic lighting, ray tracing.
Now, having this complex structure leads to one of the coolest secrets in the manufacturing world. I mean, when you're working with billions of microscopic transistors, some mistakes are bound to happen. So instead of throwing away a whole chip because a few parts are faulty, companies use a brilliant process called chip binning. They just test the chip, find the broken parts, turn them off, and then sell it as a slightly less powerful version.
And this table shows you exactly how that works. A top-of-the-line RTX 3090 Ti gets a perfect chip with all 10,752 CUDA cores working. But the 3090, the 3080 Ti, and the 3080, they're using the exact same physical piece of silicon. The only difference is that they have a few of their defective core clusters disabled. It's an incredibly smart way to make sure almost nothing goes to waste.
Okay, so we have the hardware, right? This massive army of thousands of simple cores. But how do they actually pull off those 36 trillion calculations? Well, the secret isn't just in the hardware. It's in the strategy. And that strategy is called parallelism. GPUs are purpose-built to solve a very specific kind of problem, and that kind of problem has a fantastic technical name. It's called embarrassingly parallel. Yeah, it sounds a little funny, but all it means is a huge job that can be super easily broken down into thousands of tiny, identical tasks that can all be done at the same time without having to talk to each other. And it just so happens that computer graphics is the perfect example of this. The method they use to do this is called SIMD, which stands for Single Instruction, Multiple Data. And this, right here, this is the magic trick. It's the secret sauce of the GPU. You create one simple instruction, like add 5 to this number, and then you just broadcast that single instruction to thousands of cores, and they all do it at the exact same time on their own piece of data. Let's make that real with an example. Say you have a 3D model of a cowboy hat, and it's made up of 14,000 little points. Now the old way with the CPU would be to say, move point 1. Okay, now move point 2. Okay, now move point 3. But with a GPU, you just shout one command, hey everyone, move your assigned point from here to there. Thousands of cores hear that one command and boom, all at once they move their 1 point. In a fraction of a second, the entire 14,000 point hat just appears exactly where it's supposed to be. That is the incredible power of SIMD.
So you can see how this is a total game changer for games. But it didn't take long for people to realize that this incredible power could be used for a lot more than just pretty graphics.
Remember the whole Bitcoin mining craze? Well, at its heart, mining is just trying to guess a specific number. You do that by running the same math formula over and over with a different random guess each time. It's a perfect, embarrassingly parallel job. So each little core on a GPU became its own tiny lottery ticket generator, all of them guessing different numbers at the same time, hoping to hit the jackpot.
And the AI revolution that's happening right now, it is built entirely on this same foundation of parallelism. Training a large language model means doing trillions of calculations on these giant spreadsheets of numbers called matrices. It's yet another perfect job for our cargo ship GPU, where thousands of those specialized tensor cores can chew through those massive calculations all at once. Modern AI literally wouldn't be possible without them.
So, if you take away one thing, let it be this. A GPU isn't more powerful than a CPU because its cores are smarter. It's the complete opposite. The power comes from having an enormous army of simple, specialized workers. The CPU is like a handful of brilliant engineers solving really complex, different problems one by one. The GPU is a giant factory floor with thousands of workers, each doing one small, repetitive task, all in perfect unison. It is the absolute mastery of parallelism. From video games that look like movies, to discovering new medicines, to creating powerful AI, this ability to crush massive parallel problems has already transformed our world. And it just leaves you wondering, with this power growing every single year, what new, incredible things will we be able to create? What comes next?